Word. Cool. All right. Welcome back to Crafting Interpreters in Rust. Starting today reading chapter 5. So I'll just go ahead and get started. This is on parsers. So in the last chapter, we took the raw source code as a string and transformed it into a slightly higher level representation, a series of tokens. The parser we'll write in the next chapter takes those tokens and transforms them yet again into an even richer, more complex representation. Before we can produce that representation, we need to define it. That's the subject of this chapter. Along the way, we'll cover some theory around formal grammars, feel the difference between functional and object-oriented programming, go over a couple of design patterns, and do some metaprogramming. Before we do all that, let's focus on the main goal, a representation for code. It should be simple for the parser to produce and easy for the interpreter to consume. If you haven't written a parser or interpreter yet, those requirements aren't exactly illuminating. Maybe your intuition can help. What is your brain doing when you play the part of a human interpreter? How do you mentally evaluate an arithmetic expression like this? Because you understand the order of operations, the old PEMDAS stuff, you know that the multiplication is evaluated before the addition or subtraction. One way to visualize that precedence is using a tree. Leaf nodes are numbers, and interior nodes are operators with branches for each of their operands. In order to evaluate an arithmetic node, you need to know the numeric values of its subtrees, so you have to evaluate those first. That means working your way from the leaves up to the root, a post-order traversal. All right, starting with a full tree, evaluate the bottommost expression, 2 star 3, and evaluate plus, then the minus, and the final answer. If I gave you an arithmetic expression, you could draw one of these trees pretty easily. Given a tree, you can evaluate it without breaking a sweat. So it intuitively seems like a workable representation of our code is a tree that matches the grammatical structure, the operator nesting of the language. We need to get more precise about what that grammar is then. Like lexical grammars in the last chapter, there's a long ton of theory about syntactic grammars. We're going into that theory a little more than we did when scanning because it turns out to be a useful tool throughout much of the interpreter. You start by moving one level up the Chomsky hierarchy. Let's see. I don't know if he'll actually define what Chomsky hierarchy is. Probably. In the last chapter, the formalism we used for defining the lexical grammar, the rules for how characters get grouped into tokens, was called a regular language. That was fine for our scanner, which emits a flat sequence of tokens. But regular languages aren't powerful enough to handle expressions which can nest arbitrarily deeply. We need a bigger hammer, and that hammer is a context-free grammar. It's the next heaviest tool in the toolbox of formal grammars. A formal grammar takes a set of atomic pieces it calls its alphabet. Then it defines a usually infinite set of strings that are in the grammar. Each string is a sequence of letters in the alphabet. I'm using all those quotes because the terms get a little confusing as you move from lexical to syntactic grammars. In our scanner's grammar, the alphabet consists of individual characters, and the strings are the valid lexemes, roughly words. In the syntactic grammar we're talking about now, we're at a different level of granularity. Now each letter in the alphabet is an entire token, and a string is a sequence of tokens, an entire expression. So maybe a table will help. So that is what he just said, yes. A formal grammar's job is to specify which strings are valid and which aren't. If we were defining a grammar for English sentences, eggs are tasty for breakfast would be in the grammar, but tasty breakfast for our eggs would probably not. Rules for grammars. How do we write down a grammar that contains an infinite number of valid strings? We obviously can't list them all out. Instead, we can create a finite set of rules. You can think of them as a game that you can play in one of two directions. If you start with the rules, you can use them to generate strings that are in the grammar. Strings created this way are called derivations because each is derived from the rules of the grammar. In each step of the game, you pick a rule and follow what it tells you to do. Most of the lingo around former grammars comes from playing them in this direction. Rules are called productions because they produce strings in the grammar. Each production in a context-free grammar has a head, its name, and a body, which describes what it generates. In its pure form, the body is simply a list of symbols. Symbols come in two delectable flavors. A terminal is a letter from the grammar's alphabet. You can think of it like a literal value. In the syntactic grammar we're defining, the terminals are individual lexemes, tokens coming from the scanner like if or 1, 2, 3, 4. These are called terminals in the sense of an endpoint because they don't lead to any further moves in the game. You simply produce that one symbol. A non-terminal is a named reference to another rule in the grammar. It means play that rule and insert whatever it produces here. In this way, the grammar composes. There's one last refinement. You may have multiple rules with the same name. When you reach a non-terminal with that name, you are allowed to pick any of the rules for it, whichever floats your boat. To make this concrete, we need a way to write down these production rules. People have been trying to crystallize grammar all the way back to Panini's Ashtadhyayi, which codified Sanskrit grammar a mere couple thousand years ago. Not much progress happened until John Backus and company needed a notation for specifying Algol 58 and came up with Backus-Naur form, BNF. Since then, nearly everyone uses some flavor of BNF tweaked to their own tastes. I tried to come up with something clean. Each rule is a name, followed by an arrow, followed by a sequence of symbols, and finally ending with a semicolon. Terminals are quoted strings, non-terminals are lowercase words. Using that, here's a grammar for breakfast menus. So you can see sort of how it works. Breakfast is a non-terminal, and it can be turned into any of one of these other sequences. So another non-terminal, and then here's a terminal. We can use this grammar to generate random breakfasts. Let's play around and see how it works. By age-old convention, the game starts with the first rule in the grammar. Here, breakfast. There are 3 productions for that, and we randomly pick the first one. The resulting string looks like protein with breakfast on the side. We need to expand that first non-terminal, protein, so we pick a production for that. Let's pick protein to cooked eggs. Next, we need a production for cooked, so we pick poached. That's a terminal, so we add that. Now our string looks like poached eggs with breakfast on the side. Next non-terminal is breakfast again. The first breakfast production we chose recursively refers back to the breakfast rule. Or recursively refers back to the breakfast rule. Recursion in the grammar is a good sign that the language being defined is context-free instead of regular. In particular, recursion where the recursive non-terminal has productions on both sides implies that the language is not regular. We could keep picking the first production for breakfast over and over again, yielding all manner of breakfasts like bacon with sausage with scrambled eggs with bacon. We won't though. This time we'll pick bread. There are 3 rules for that, each of which contains only a terminal. We'll pick English muffin. So bread, English muffin. With that, every non-terminal in the string has been expanded until it finally contains only terminals, and we're left with this tree here. Throw in some ham and hollandaise, and you've got Eggs Benedict. Anytime we hit a rule that had multiple productions, we just picked one arbitrarily. It is this flexibility that allows a short number of grammar rules to encode a combinatorially larger set of strings. The fact that a rule can refer to itself, directly or indirectly, kicks it up even more, letting us pack an infinite number of strings into a finite grammar. Stuffing an infinite set of strings in a handful of rules is pretty fantastic, but let's take it further. Our notation works, but it's tedious. So like any good language designer, we'll sprinkle a little syntactic sugar on top, some extra convenience notation. In addition to terminals and non-terminals, we'll allow a few other kinds of expressions in the body of a rule. Instead of repeating the rule name each time we want to add another production for it, we'll allow a series of productions separated by a pipe. Bread can be any of these things. Further, we'll allow parentheses for grouping and then allow pipe within that to select one from a series of options within the middle of a production. Using recursion to support repeated sequences of symbols has a certain appealing purity, but it's kind of a chore to make a separate named subrule each time we want to loop. So we use a postfix star to allow the previous symbol or group to be repeated 0 or more times. A postfix plus is similar, but it requires the preceding production to appear at least once. It's just like regular expression rules. A postfix question mark is for an optional production. Thing before it can appear 0 or 1 time, but not more. And with all of these syntactic niceties, our breakfast grammar condenses down to protein with breakfast on the side, maybe, or bread, and so on. Not too bad, I hope. If you're used to grep or using regular expressions in your text editor, most of the punctuation should be familiar. The main difference is that symbols here represent entire tokens, not single characters. We'll use this notation throughout the rest of the book to precisely describe Lox's grammar. As you work on programming languages, you'll find that context-free grammars, including using this or eBNF or some other notation, help you crystallize your informal syntax design ideas. They are also a handy medium for communicating with other language hackers about syntax. The rules and productions we define for Lox are also our guide to the tree data structure we're going to implement to represent code in memory. Before we can do that, we need an actual grammar for Lox, or at least enough of one for us to get started. A grammar for Lox expressions. In the previous chapter, we did Lox's entire lexical grammar in one fell swoop. Every keyword and bit of punctuation is there. The syntactic grammar is larger, and it would be a real bore to grind through the entire thing before we actually get our interpreter up and running. Instead, we'll crank through a subset of the language in the next couple of chapters. Once we have that mini language represented, parsed, and interpreted, then later chapters will progressively add new features to it, including the new syntax. For now, we are only going to worry about a handful of expressions: literals, unary expressions, binary expressions, parentheses. Okay, that gives us enough syntax for expressions like this. Using our handy-dandy new notation, here's the grammar for those. So we've got expression, can go to any one of these options. Yeah. Grouping means parentheses, unary means this. Yeah. There's one bit of extra meta syntax here. In addition to quoted strings for terminals that match exact lexemes, we capitalize terminals that are a single lexeme whose text representation may vary. Number is any number literal, and string is any string literal. Later, we'll do the same for identifier. This grammar is actually ambiguous, which we'll see when we get to parsing it, but it's good enough for now. Implementing syntax trees. Finally, we get to write some code. That little expression grammar is our skeleton. Since the grammar is recursive, note how grouping, unary, and binary all refer back to expression, our data structure will form a tree. Since this structure represents the syntax of our language, it's called the syntax tree. Our scanner used a single token class to represent all kinds of lexemes. To distinguish the different kinds, think the number 123 versus the string 123, we included a simple token type enum. Syntax trees are not so homogeneous. Unary expressions have a single operand, binary expressions have 2, and literals have none. We could mush that all together into a single expression class with an arbitrary list of children. Some compilers do, but I like getting the most out of Java's type system. So we'll define a base class for expressions. Then for each kind of expression, each production under expression, we create a subclass that has fields for the non-terminal specific to that rule. This way we get a compile error if we say try to access the second operand of a unary expression. Okay. Yeah, so this is how we did it in like when I took a compilers class. We also did like implemented the thing in Java, and then each type of node in the AST had like a couple precise fields. I'm kind of wondering how much we can get away with using just like a sum type in Rust for these instead of a whole list of classes. I don't know how differently they're going to have to act, really. So, okay. Expr is the base class that all expression classes inherit from. As you can see from binary, the subclasses are nested inside of it. There's no technical need for this, but it lets us cram all of the classes into a single Java file. Disoriented objects. You'll note that much like the token class, there aren't any methods here. It's a dumb structure, nicely typed, but merely a bag of data. This feels strange in an object-oriented language like Java. Shouldn't the class do stuff? The problem is that these tree classes aren't owned by any single domain. Should they have methods for parsing since that's where the trees are created? Or interpreting since that's where they're consumed? Trees span the border between those territories, which means they are really owned by neither. In fact, these types exist to enable the parser and interpreter to communicate. That lends itself to types that are simply data with no associated behavior. This style is very natural in functional languages like Lisp and ML, where all data is separate from behavior, but it feels odd in Java. Functional programming aficionados right now are jumping up to exclaim, "See, object-oriented languages are a bad fit for an interpreter." I won't go that far. You'll recall that the scanner itself was admirably suited to object orientation. It had all of the mutable state to keep track of where it was in the source code, a well-defined set of public methods, and a handful of private helpers. My feeling is that each phase or part of the interpreter works fine in an object-oriented style. It is the data structures that flow between them that are stripped of behavior. Metaprogramming the trees. Interesting. Java can express behaviorless classes, but I wouldn't say that it's particularly great at it. 11 lines of code to stuff 3 fields in an object is pretty tedious, and when we're all done, we're going to have 21 of these classes. I don't want to waste your time or my ink writing that all down. Really, what is the essence of each subclass? A name and a list of typed fields. That's it. We're smart language hackers, right? Let's automate. Instead of tediously handwriting each class definition, field declaration, constructor, and initializer, we'll hack together a script that does it for us. It has a description of each tree type, its name and fields, and prints out the Java code needed to define a class with that name and state. The script is a tiny Java command line app that generates a file called expr.java. All right. Note that this file is in a different package, .tool instead of .lox. This script isn't part of the interpreter itself. It's a tool we, the people hacking on the interpreter, run ourselves to generate the syntax tree classes. When it's done, we treat expr.java like any other file in the implementation. We are merely automating how that file gets authored. To generate the classes, it needs to have some description of each type and its fields. Okay. For brevity's sake, I jammed the descriptions of the expression types into strings. Each is the name of the class followed by colon and the list of fields separated by commas. Each field has a type and a name. The first thing define AST needs to do is output the base expert class. So we're going to literally write out the Java code that is here.
Okay, I don't think we should go this way.
No.
We can use macros.
Macros? Yeah.
Yeah.
So yeah, like a macro where we define the grammar in like this sort of notation.
Sort of, yes.
What's the reasoning for not going the other way?
It's just I mean, Java is kind of limited language, and Rust, you have this nice tool to generate boilerplate for you.
Yeah, macros are the same, are Rust's way of doing the same thing as code generation. Code generation is like kind of brute force.
Our goal is
Yes.
not just to build the interpreter, but also to learn something from it. Maybe people don't know how to deal with macros, so that might be interesting.
Yeah.
Like both type, like what the declarative and procedural macros we would use, or
I think we'll use just declarative for now.
Okay.
Procedurals are they similar, but
keeping
hard
it
to use.
a little
Trying to
simpler.
think.
Okay.
Yeah, we'll see when we get there. I think, yeah, let's see exactly what kind of like code generation he needs to do. So he needs to have base name, class name, field list. Yeah, I think if declarative macros can handle like lists of things and then like iterate over them, then we can do it in a declarative macro. I think they can.
Well, it's not going to be iteration, but it can do lists of items. Yes,
Like a
processing.
expand out.
Yep.
Yeah. Cool.
Are we? I was just curious if we're going to need to be able to do a recursion for some of the expressions, or is that?
So yes, because some of the classes can contain, like the expression can contain another expression, I believe.
Yeah.
Or yeah, at the very least, expression can contain a grouping, and grouping can contain an expression. So, I mean, that doesn't imply that you need recursion in the macro, because it's just like string replacement. But
Okay.
yeah, these classes do recursively refer to each other. Okay. All right. So blah blah blah. He does the code generation in Java. So pass base name as an argument. And then what are we doing here? So write the expr boilerplate. And then for each type, you figure out this is parsing his like little colon format here. So parse that and figure out the class name and the fields from that, and then write the boilerplate for that particular class. And that's what this will do. So write the declaration, and then for each field, you do the whole this dot field equals field in the constructor. Yep. It's kind of funky. I've done this in Python once, like use Python to generate C++. It was weird. Basically the same thing. All right, there we go. All of that glorious Java boilerplate is done. It declares each field in the class body. It defines a constructor for the class with parameters for each field and initializes them in the body. Compile and run this Java program now, and it blasts out a new .java file containing a few dozen lines of code. That file is about to get even longer. Put on your imagination hat for a moment. Even though we aren't there yet, consider what the interpreter will do with the syntax trees. Each kind of expression in LOX behaves differently at runtime. That means the interpreter needs to select a different chunk of code to handle each expression type. With tokens, we can simply switch on the token type, but we don't have a type enum for the syntax trees, just a separate Java class for each one. We could write a long chain of type tests. All right, if X per instance of binary, etc. But all of these sequential type tests are slow. Expression types whose names are alphabetically later would take longer to execute because they'd fall through more if cases before finding the right type. That's not my idea of an elegant solution. We have a family of classes and we need to associate a chunk of behavior with each one. The natural solution is an object-oriented language, or in an object-oriented language like Java, is to put those behaviors into methods on the classes themselves. We could add an abstract interpret method on Xper, which each subclass would then implement to interpret itself. Okay. This works all right for tiny projects, but it scales poorly. Like I noted before, these tree classes span a few domains. At the very least, both the parser and interpreter will mess with them. As you'll see later, we need to do name resolution on them. If our language was statically typed, we'd have a type checking pass also. If we added instance methods to the expression classes for every one of those operations, that would smush a bunch of different domains together. That violates separation of concerns and leads to hard to maintain code. The expression problem. This problem is more fundamental than it may seem at first. We have a handful of types and a handful of high-level operations like interpret. For each pair of type and operation, we need a specific implementation. Picture a table. Rows are types and columns are operations. Each cell represents the unique piece of code to implement that operation on that type. An object-oriented language like Java assumes that all of the code in one row naturally hangs together. It figures all the things you do with the type are likely related to each other, and the language makes it easy to define them together as methods inside the same class. This makes it easy to extend the table by adding new rows. Simply define a new class. No existing code has to be touched. But imagine if you want to add a new operation, a new column. In Java, that means cracking open each of those existing classes and adding a method to it. Functional paradigm languages in the ML family flip that around. There, you don't have classes with methods. Types and functions are totally distinct. To implement an operation for a number of different types, you define a single function. In the body of that function, you use pattern matching, sort of a type-based switch on steroids, to implement the operation for each type all in one place. This makes it trivial to add new operations. Simply define another function that pattern matches on all of the types. But conversely, adding a new type is hard. You have to go back and add a new case to all of the pattern matches in all of the existing functions. Each style has a certain grain to it. That's what the paradigm name literally says. An object-oriented language wants you to orient your code along the rows of types. A functional language instead encourages you to lump each column's worth of code together into a function. A bunch of smart language nerds noticed that neither style made it easy to add both rows and columns to the table. They called this difficulty the expression problem because, like we are now, they first ran into it when they were trying to figure out the best way to model expression syntax tree nodes in a compiler. People have thrown all sorts of language features, design patterns, and programming tricks to try to knock that problem down, but no perfect language has finished it off yet. In the meantime, the best we can do is try to pick a language whose orientation matches the natural architectural seams in the program we're writing. Object orientation works fine for many parts of our interpreter, but these tree classes rub against the grain of Java. Fortunately, there's a design pattern we can bring to bear on it, the visitor pattern. The visitor pattern is the most widely misunderstood pattern in all of design patterns, which is really saying something when you look at the software architecture excesses of the past couple of decades. The trouble starts with terminology. The pattern isn't about visiting, and the accept method in it doesn't conjure up any helpful imagery either. Many think the pattern has to do with traversing trees, which isn't the case at all. We are going to use it on a set of classes that are tree-like, but that's a coincidence. As you'll see, the pattern works as well on a single object. The visitor pattern is really about approximating the functional style within an OOP language. It lets us add new columns to that table easily. We can define all of the behavior for a new operation on a set of types in one place without having to touch the types themselves. It does this the same way we solve almost every problem in computer science, by adding a layer of indirection. Before we apply it to our auto-generated expression classes, let's walk through a simpler example. Say we had two kinds of pastries, beignets and crullers. We want to be able to define new pastry operations, cooking them, eating them, decorating them, etc., without having to add a new method to each class every time. Here's how we do it. First, we define a separate interface, so a pastry visitor, and it has a visit beignet and visit cruller. And both of these take the type that they correspond to. Each operation can be performed on pastries is a new class that implements that interface. It has a concrete method for each type of pastry. That keeps the code for the operation on both types all nestled snugly together in one class. Given some pastry, how do we route it to the correct method on the visitor based on its, the correct method on the visitor based on its type? Polymorphism to the rescue. We add this method to pastry. So it will have accept, which takes a visitor. Each subclass implements it. Okay. So in beignet, you will have an accept, which takes a visitor, and then that's how it tells it, and then calls the beignet method on it. Okay. To perform an operation on a pastry, we call its accept method and pass in the visitor for the operation we want to execute. The pastry, the specific subclass's overriding implementation of accept, turns around and calls the appropriate visit method on the visitor and passes itself to it. That's the heart of the trick right there. It lets us use polymorphic dispatch on the pastry classes to select the appropriate method on the visitor class. Yeah, there's the indirection. In the table, each pastry class is a row, but if you look at all the methods for a single visitor, they form a column. We added one accept method to each class, and we can use it for as many visitors as we want without ever having to touch the pastry classes again. It's a clever pattern. Okay, let's weave it into our expression classes. We'll also refine the pattern a little. In the pastry example, the visit and accept methods don't return anything. In practice, visitors often want to define operations that produce values. But what return type should accept have? Excuse me. We can't assume every visitor class wants to produce the same type, so we'll use generics to let each implementation fill in a return type. First, we define the visitor interface. Again, we nest it inside the base class so that we can keep everything in one file. So define visitor. This appears to be part of the code generation thing. Yeah. So they are writing out literally interface visitor for some R. And then defining a visit function on it. Yeah, okay. Oh, R is the return type here. Here we iterate through all of the subclasses and declare a visit method for each one. When we define new expression types later, this will automatically include them. Inside the base class, we define the abstract accept method. Finally, each subclass implements that and calls the right visit method for its own type. Okay, yep. And this is again, this is fine in macros, I think. We won't, I don't know if we will need the visitor pattern. I'll think about it.
So our goal is to keep the language as consistent as possible with the book.
Yeah, it's going to be the And it's going to do the same thing, right?
Yeah.
Just, you know,
Language, yes, implementation, we have a few differences already, like for scanner, we use iterator.
yeah,
So we
right.
need to pick corresponding abstraction from Rust and try to use that.
Right. Yeah. I mean, there's nothing, the visitor pattern is not super complicated. I'm just wondering if there's some more clever thing that exists in Rust type system. I haven't thought of it yet. Okay, there we go. Now we can define operations on expressions without having to muck with the classes or our generator script. Compile and run this generator script to output an updated expr.java file. It contains a generated visitor interface and a set of expression node classes that support the visitor pattern using it. Before we end this rambling chapter, let's implement that visitor interface and see the pattern in action. A not very pretty printer. When we debug our parser and interpreter, it's often useful to look at a parsed syntax tree and make sure it has the structure we expect. We could inspect it in the debugger, but that can be a chore. Instead, we'd like some code that, given a syntax tree, produces an unambiguous string representation of it. Converting a tree to a string is sort of the opposite of a parser and is often called pretty printing, when the goal is to produce a string of text that is valid syntax in the source language. That's not the goal here. We want the string to very explicitly show the nesting structure of the tree. A printer that returned 1 plus 2 or 1 plus 2 star 3 isn't super helpful if what we're trying to debug is whether the operator precedence is handled correctly. We want to know if the plus or star is at the top of the tree. To that end, the string representation we produce isn't going to be lock syntax. Instead, it will look like a lot like Lisp. Each expression is explicitly parenthesized, and all of its sub-expressions and tokens are contained in that. Given a syntax tree like this, it produces this prefix notation locks thing, or well, Lisp looking thing. Not exactly pretty, but it does show the nesting and grouping explicitly. To implement this, we define a new class. So we will make an AST printer that implements the visitor pattern interface. And so print just calls accept on the okay, that makes sense. So as you can see, it implements the visitor interface. That means we need to visit visit methods for each of the expression types we have so far. So, yeah, these return what? Strings? Yeah, just strings. Literal expressions are easy. They convert the value to a string with a little check to handle Java's null, standing in for Lox's nil. Okay, so visit literal expression. If it's nil, or if it's Java null, we're using that to stand in for Lox nil, so return nil. Otherwise, return parsed thing. The other expressions have sub-expressions, so they use this parenthesize helper method, which will just recursively call except on their sub-expressions, but then wrap it in parentheses. It takes a name and a list of sub-expressions and wraps them all up in parentheses, yielding a string like +1, 2. Note that it calls except on each sub-expression and passes in itself. This is the recursive step that lets us print an entire tree. What is this here? I guess that's the visitor. Yeah. So the visitor, it's passing itself down to the child nodes of each node. So it's when it calls accept. All right. We don't have a parser yet, so it's hard to see this in action. For now, we'll hack together a little main method that manually instantiates a tree and prints it. All right, so they make a tree. or an expr, the root node, and then they print it out. If we did everything right, it prints this thing. You can go ahead and delete this method. We won't need it. Also, as we add new syntax tree types, I won't bother showing the necessary visit methods for them in AST printer. If you want to, and you want the Java compiler to not yell at you, go ahead and add them yourself. It will come in handy in the next chapter when we start parsing LOX code into syntax trees. Or if you don't care to maintain AST printer, feel free to delete it. We won't need it again. I'm not sure whether I want it or not. Okay. Let's see, where are we on time? I kind of doubt we can get anywhere. Maybe we can start this macro that we were talking about. Might be fun.
Before making macro, I usually try to come up with code I'm going to generate for that.
Mhm.
So we can take like 2 or 3 data types, for example, for these math expressions, and implement it by hand.
Right. Okay. Yeah. So I guess we will have. So here's what I was wondering. Do we actually need like separate structs for any of these like expression types or node AST node types, or can we just use one like enum node type?
I think we can use maybe not one enum type. So for example, for if expressions, we'll know that the first parameter is Boolean and the remaining 2 parameters are like arbitrary expressions. I don't know, are we going to add any type safety for that, or is it? Did anybody went this far into the book?
Sorry, type safety for what?
Well,
If
I guess we can try this single node type expression. We'll see.
so, okay. Yeah. Okay. Do it. Is it? I forgot what the convention is.
Are we going to use this, or is it easier just to make our usual enum sum type that will contain the fields directly?
That's what I was wondering. Like,
But
I guess. Oh wait, these are not the same thing as
yeah, how would it contain the fields if it's like rules of a function? I mean, almost like where it has recursion.
It starts as a set of rules, but what gets generated is more like expressions.
All right, let's think about this. So he is generating a bunch of classes, each of which have some fields, and the field type is like this base class here.
Yep.
Or
We can simply have enum type called expression with fields like literal, unary, binary, and recursive in the right places.
okay. So unary will have another expression inside of it, right?
Can you have the defining enum? Well, I guess we could try.
Yeah.
See if
You
it's
need to box it.
like with a dynamic.
No, it's not dynamic when you try to make recursive data type without explicit boxing. Rust is trying to inline it, and that leads to infinite
Yeah.
data type size.
Okay.
So I guess these the subfields aren't named here. I guess it has an operator. How does this even work? Like, so, because this is like this is the parent type. We need to say specifically there's an operator here at this position.
Yeah, Michael earlier was talking about making an enum for expression.
Yeah.
And so you could have on the unary, you could have a tuple, and one might be a Boolean, whether it's, minus or not. And then the other one could be an expression.
So second field in unary branch is box node type, but the first field needs to be either minus or exclamation mark.
Yeah.
Yeah, I would say that the second field needs to be box expression, where expression is a separate enum.
Okay. So in that case, is it like one enum per thing that gets referenced here? So there's like an enum.
Yeah, it seems reasonable.
And then enum operator.
I guess so.
Call it unary operator and have it have two
Sure.
variants.
Yeah. So enum and then binary operator has like all of these. I guess, how are we encoding which variant means which string? How does he do that?
We can implement from string. Actually, we have it in the tokenizer, so all we need to do is to implement try from.
Okay, and that's for everything.
That's for parse. Yeah.
Everything that is a node needs that. So we need to make a separate impl for each of these enums.
Yeah. Well, let's make something simple. Like we need expression, we need binary and unary. Let's start with that.
Sure. So binary contains another expression, a binary operator, and an expression.
Well, if we want to copy the structure he has directly, binary branch can contain binary thingy inside.
So I would not do that. Instead, I do an all caps binary, and then in parentheses, I put up upper camel case binary.
What here?
Yeah, and then in parentheses, put an upper camel case binary.
There is a link to
I want to call
Editor,
this.
by the way. You can connect and try to type it yourself.
What's that? Oh, you're saying the live?
Yeah,
Live
the
session?
live
Yeah.
view.
The link is earlier in the chat. The prod.liveshare.whatever URL. So can you explain
Yeah,
the
so
naming scheme here? So like unary, the variant.
so binary is
unary,
your
the node
variant.
type. Yeah.
Binary all caps is your variant, and then it has a tuple, and the content of the tuple is an enum binary.
Mm-hmm. And then what an enum,
And
this
an
has,
enum binary is, is made up of expression in all caps with a tuple with, and then in parentheses, expression upper camel case. And then operator and then expression.
there's
So-
only one variant of binary though.
Yeah, so here you'd have like expression 0 or expression 1, an operator and expression 2. But expression 1 and expression 2, those variants would each have a tuple of type enum expression.
Mm-hmm. I guess like so there's each enum variant is like one of these rules. Or like one of the production rules. So operator has however many this is variants. But binary only has one because it can only turn into this sort of thing, expression and then operator and then expression. So is that even an enum? Like, and same with grouping and unary.
Let's see what would the other choice for data types that would be for binary if it's just a structure or something, or
Yeah. I guess I'm trying to keep it sort of uniform so that we can easily generate it with a macro from the grammar. Yeah, it's weird. So this can also be a literal. Yeah, so this is like the pattern I'm trying to. Okay, right box. So every. Oh, it needs to, yeah, okay, so I see what's going on. So unary will have like variants for this or that. And then literal needs variants. We need another thing, enum literal, which has variants for like each of these. And it's whatever we used last time. I think F64, yeah. And, yeah, true, false, no. And then this introduces lifetime things again. And then this
can
will
make it
be,
a known string.
this will be like whatever we call them, like neg or bang or something like that. Oh, dash or something. Actually, yeah, where's the token type for oh, it's minus, it's gonna be minus. Yeah. I think this is kind of what we want.
Yeah, but I'd call that where you have unary minus and bang. I would change that to unary operator. And then unary operator would be a unary plus, a unary would then be a unary operator plus an expression.
Oh, okay. So you're saying like instead of trying to put the non-terminals all stuffed into the expression rule, just like let them be under here. Okay, I think I see what you're saying. So I guess, so here it's either like, okay, here's what
Yeah,
not,
this is
here-
either bang or, you know,
yeah,
so all you're doing is renaming what you had before.
here's what's confusing to me. So if you try to put if so, let's say if we try to do it this way, wait, are you just proposing like renaming things or reorganizing the recursive structure in some way?
It's possible. I'm suggesting both. My first initial, yeah, like on line 9 there where you have binary,
Mhm.
you know, my initial feeling was that it should be, you know, binary, box binary. But I mean, maybe we can work out gradually. We just do unary operator. We know it has 2 variants. It's either going to be the minus or the bang.
Mhm.
And then we know that a unary, okay, like you have it there. Yeah, so that feels good.
Okay. Right. So I guess, yeah, so what's weird is like, you know, if we, right now it's only like one kind of nested type. Expression is the only one that gets like recursively nested. Like operators here, but it only leads to terminals. So because of that, that's the only reason why I'm putting all like the recursive structure in the variants for expression. But if we had more than one, I don't really know how I would handle it yet. Yeah, so
The same way.
We could make a unary struct.
yeah, I don't know. Right, that's what I'm saying. It's like, yeah, right. That's the choice between the unary struct, which contains like either one of like a unary operator and a box
Yeah.
expression, or just having it as an enum variant under expression.
Yeah,
That's
where
the-
you're just using a tuple instead of struct. Yeah, so it's pretty much the same.
Well, what it matters which one is easier to describe for a macro. So let's see. So binary operator is going to be like, you know, one of these.
Well, if you had a struct and you wanted to have associative functions, you know, on like let's say you had a unary struct and you want to have an associative function on the unary struct, that could be an argument for doing it that way. And you know, one of the associative functions could be, you know, accept visitors, just as an
Yeah.
example.
Yeah. We need like, because the visitor pattern is sort of how you specify how, like how to evaluate the subfields. So I guess, right. We need some way of saying like, you know, if it's a binary expression, then call accept on these. All right. I will think about it some more. But yeah, that's cool. We made it through chapter 5. Are there
We
any
started chapter 5. We'll have to continue on it next time and probably time after that.
Yeah, this will take some workshopping for sure. Any questions about the content here? Are we?
So for like people who've had compiler classes, this is pretty like sort of how most of them are structured, or
Yeah, the constructing the AST, we definitely did using the visitor pattern.
okay.
And actually like later, so like constructing the AST or was done using visitors, and then also producing the resulting assembly code, like in a compiler. That was just another type of visitor. So yeah.
So we'll
It's-
we'll end up using the visitor pattern most likely in the Rust implementation.
Yeah, I will do it unless I can think of something like really clever.
Okay,
Get around
so
it. Yeah.
I'll have to review the visitor stuff in this book.
Mhm.
Visitor pattern. Okay. Okay, cool. Wow, this looks interesting to continue on with. You'll post are you gonna make a branch or just put this on main for like where we got to?
I'll just put it on main.
Okay.
Yeah.
Excellent.
Okay, cool. Thank you guys for the code suggestions as always. And I'll see you next time, hopefully.
Alrighty. See ya.